So we've looked at a couple of examples where we actually calculated the K value if we knew the equilibrium concentrations or if we could figure them out. Now we want to go ahead and look at some examples where we start thinking about what this K value really means to us. So the magnitude of the K value can tell us what's going on in that beaker, where the equilibrium is. When we have a large K value, it means that the concentrations of the products is greater than the concentrations of the reactants, because remember, K is products concentrations all multiplied together divided by the reactants. So in a large K value, in order for this number to be big, products concentration has to be bigger than the reactants concentration. So we say that it's a product-favored equilibrium. When we have a small K value, looking at this, in order for K to be small, the number on the bottom of the fraction has to be bigger, so the products concentration is less than the reactant concentration, so we say that we have a reactant-favored equilibrium. And then when we look at what's in between, we have a K that's about equal to 1. So when K is about equal to 1, the products and the reactant concentrations will be about the same. Now this about equal to 1 is kind of fluffy, not what we normally think. We normally would think of something close to 1 as 1, like maybe 0.9 to 1.01. But here it's about 1/100th to about 100. And I know I don't think of 100 as being close to 1, but in this context, that's what it is. And the reason for that is that you can have all kinds of exponents up here. So we take the concentrations, and if we're multiplying them by themselves 2 or 3 times, we're going to get something closer to 100 if we have all those big exponents on top. Or we can think about going towards 100th if we have those exponents on the bottom. So when we think about where the K value came from, this kind of makes sense. So now what I'd like you to do is take just a moment and look at these K values and then predict the position of the equilibrium for each of these. So look at these two, or these three, and predict the position of the equilibrium. Just pause the video while you do that. Okay, now when you look at this, 10 to the negative 21st, that K value is a small number. So this one would be reactant favored. For the next one, we have an exponent that's quite large, so K is large. So this equilibrium would be product favored. It means if you looked in the beaker with your molecule seeing eye, you'd see lots of the products and not very much reactant. And here you'd see a lot of reactant and not much product. Now looking at this one, where my K is 0.145, that's in that range of it being about 1. So these product and reactants would be about equal. So it's neither product nor reactant favored. Now earlier I told you that when we're talking about concentrations and looking at these K values, we don't include solids and we don't include pure liquids. And now I'd like to show you mathematically why that is. The reason is the concentration does not change. We're talking about the molar concentration in moles per liter. And the concentration never changes for these pure solids and liquids. So let's look at calculating the molarity of pure water. Now, we don't think about moles per liter of water, but if we think about water, we know that 1 mole of water has a mass of 18 grams. And we know the density of water is 1 gram per milliliter. We know there's 1,000 milliliters in 1 liter. So my units of grams and milliliters cancel, and I get 56 moles per liter. So the concentration of water, the molar concentration, is 56 moles per liter. And this doesn't change. If you have a bucket of water, a drop of water, or an ocean of water, it still has the same molar mass, it still has the same density, and it still has the same conversion from liters to milliliters. Since this never changes, we know that our K value is equal to the product's concentration divided by the reactant's concentration. If this number, which never changes, is in here, we can think of it as a constant. So all we need to do is divide it and wrap it into the constant, and that's why we don't put the solids and liquids in, because they're incorporated in the constants.